Morning guys. So this virtual tutorial is created to allow you guys to get a better understanding of the concept of moments from start to finish. I will ask you to send it to your classmates, allow them also to check it out if they are not presently within the group, right? And if they are not in the group, allow them to come into the group. So this will suffice for a Zoom meeting that I would have loved to hold, right? And I think this is better. A Zoom is only for a one-time thing, right? If you miss it, you've missed it. But this is on YouTube and you can access it whenever you want. Alright, so I want to first identify what the moment of a force is by definition. I'm going to introduce you to two definitions. The first one is the moment of a force can be defined as the turning effect of the force. So if a force is acted upon in a manner that it effects turning, right, or is angled in a manner that will direct in a turn, then it can be classified as the moment of that force. What do I mean? The second definition is more detailed. So the second definition says a moment of a force can be defined as also the product, which, as we know from we hear the word product, we know multiplication comes in, right? The product of the magnitude of the force, which is in newtons, and the perpendicular distance. You know that perpendicular distance pertains to a 90-degree angle, right? By now, the perpendicular distance. So this distance is 90 degrees away from the force itself, right? And this perpendicular distance is measured from the pivot, which is the turning point. Other terms for turning point can be fulcrum, that you've learned from grade 6, axis, right? So those are terms that can be used. So you have fulcrum, axis, pivot, and turning point. All of those four mean the same thing. To the line of action of the force. So the line of action of the force is actually where the force is being applied, right? So let's go over that once more again. The product, the moment of a force can either be defined as the turning effect of the force or as the product of the magnitude of the force and the perpendicular distance. So that is force times distance right there, from the pivot, which is the turning point, to the line of action of the force. And line of action of the force right here would be this. The force can either be applied upwards or downwards, right? And it must be from a distance that is 90 degrees away from it. Okay? You seeing that? 90 degrees away from it. Alright? So that is force, that is moments of a force defined. Not just the force, but the force that will be multiplied by the distance, 90 degrees away from it. To understand more about moments, you must understand the unit of moments. The unit of moment is called the Newton meter, which has the symbol capital N and beside it common M. The N refers to the Newton and the M refers to the meter. So this tells us, and I hope bright students will know, that it tells us that the unit of moments is a derived unit. It's a derived unit, guys. Right? Therefore, it is derived from two things: the Newton, in which force is measured, and the meter, in which distance is measured. Okay? So it is a derived quantity. Alright? Now, even in looking at it, we can understand and appreciate how we even will come about even the equation for calculating moments. For when you see these two things that are different units beside each other, it is telling you, when they are arranged like that, it is telling you that they are multiplying each other, and that I just put there refers to multiplication. Therefore, N times M. N Newton times meter would give you the moment, and that is where we'll be going into. Okay, when you're doing moments also, you must understand something that should be in the back of your minds when you're actually attempting a question, and it is a term called equilibrium. What? Librium. Alright, so what does that mean? I know that you know about prefixes from English class. Equi means equal or balance. Librium means state. So equilibrium means a balanced state. Right? And this is how you can even help yourself in English class. If you know what piece of the word means or the prefix in the word, then you can basically find out what the word actually means and make more sense of the word. So this is defined as the state in which a body, and a body in this case can mean a ruler that you're trying to find the moment of, right? Or a meter ruler, also a meter rule, or a door with a hinge on it that is attached to a door jamb. It can be a wrench, right? A pliers that you're using to untighten a bolt. So wide range of items. Wherever, all of those things are called the body. Is not changing in composition, position, shape, or movement. So a nice analogy or diagram that shows this is this little seesaw that I have drawn here, right? So we have a force here, F1, that is a certain distance x away from the pivot, and the pivot is right there. It's always the turning point. It may not be in the direct middle all the while, you must understand that, right, as the questions will change, right? But it is always where the turning action is occurred. So on the seesaw, force 1 here, force 2 there, right? Also y distance away from the pivot, always measured away from the pivot, right? As that is what we, as we had identified, is the line of action of the force. Okay, guys? Now, when we're basically looking at that, we see that we have a balanced seesaw here. We do not see something that is like that, right? We do not see that. We see something that is in a straight line. Why is it straight? Why is it balanced? Why is it not toppling over, right? This is because the force multiplied by here, by this distance, gives you a moment that is equal also to the moment that you will get when you calculate this force times that distance. Though the distances and the forces may be different, but by the time you calculate and you find the moment over here, and you find the moment over here, you're going to find out say the same moment you have, therefore you have a balanced state. Do you understand where I'm coming from? Okay, guys. So let's look on two factors that affects the moment of a force. Alright, so there are principally two factors that affect it. Firstly, the size, which is also called the magnitude. For your size, you know, size is interchangeable for the word magnitude, right? So the size of the force. How big is the force? That quantity affects the moment of the force. And secondly, the distance, or how far away the force is from the pivot, which is also the turning point. Okay, so two things. The factors that affect the moment of a force are one, the size of the force, and also the distance, how far is the force away. And you will see this coming out in the calculations, right? So there we have a distance. Say for instance, along that distance we have a force being applied here, downward, right? And right here would be the turning point, okay? And if you see, the force is acting 90 degrees away from the distance, okay? There you would have it. So that is a nice example to see. The bigger the force is, the greater the moment will be. The lesser the force is, the lesser the moment will be. The greater the distance is, the greater the moment will be. The lesser the distance is, the lesser the moment will be. And you will see that coming out in the calculations. Alright? Okay, guys, so let's look at some examples of moments in real life. So examples of moment in real life. So guys, you have been actually using the occurrence of moments from you were somebody. Okay, you just didn't know it. Alright, so we're going to look at 3 applications of moments and see in which we can basically understand more about moments, okay? And moments is also actually referred to as torque. Torque. T-O-R-Q-U-E. You're going to see that when I start to keep a lot. The term there is not really used at CXC, but really and truly, I see him. Alright, so first example is that we're going to look at a spanner that loosens a nut. all of you must have seen a spanner in a real life or a pliers. Me sure say none of you never see a nut on your bicycle or has seen it on a car wheel and have ever dared to try to unscrew it with your finger. I know that none of you would ever try to do that, to actually loosen a tight nut with your finger. Why is it though that you can use a spanner? Look at this spanner. It doesn't have any mechanism for tightening on it. All it is just there, a piece of metal will shape out. And you put it around the nut and you put your hand on it and you use less energy, guys. You would have gone to the nut. I try and you can't do it. But as soon as I take this spanner, bop. You actually use less energy, guys. You have to agree with me. You use less energy or less force rather. You use less force to really and truly untighten that nut. Why is that so? You see, when the effort, I mean, no know about effort, that is applied here where your hand would go, right? Or the force. Effort also can be considered as the force when looking at moments, right? Remember that effort can also be considered as force. When the effort or the force is applied here, a certain distance away from the pivot is right there, which is the nut, and the nut turns, not so, right? And the nut turns, so that is the point of action, point of turning action. So pivot can be defined as the point of turning action. Make a note of that, right? So when you do that, you know what happens? The distance away that the force is being applied to the turning point actually is multiplying the amount of force. So you have the forces, say for instance you put in 5 Newton, right? You see, by the time the distance that force is worked upon by a certain distance away from the pivot, the distance multiply the force and make it actually more powerful by the time it reaches at the nut, which is the turning point, and unscrew the nut. So that is how, while you couldn't do it, because you would have to go really, really close and try to use your 5 Newton, actually more, your 10 Newton energy. But when you come right here and you put in 5 deso, and so the distance here so is like, say for instance, say for instance it is 20 centimeter long pivot, long spanner. That 20 centimeter now multiplies that 5 Newton you have put in, and you can you imagine how much force force that is now being applied to that nut right there, and it must be screw off. So that's one. Now right here now, when we go over here, second example, we are seeing a seesaw. We have big head over here, so sit down on one side. If you want to call him fathead, that's okay. And liquid. You understand? So big head and liquid, or fathead and liquid upon the seesaw. A seesaw is balanced. How come that big head so big and little head so little? Yet still big head not take down the seesaw and left big little head up in the here. How is that happening? A simple maths. I see same thing again. You see, when you're looking at situations like this one, is rather easy. Rather easy, you ask me why I say rather easy. Right? Because you only have one force applied to one pivot, to the pivot. But in this situation, and this is where we really need to approach now, we need to take into consideration something called clockwise movement and anti-clockwise movement. Okay? And we're going to go into that more. But over on the right hand side, you will have something, an occurrence called your clockwise movement. Over on the left hand side, you will always have something, called your anti-clockwise movement. Okay? Alright, good. The pivot is right there, at the base, right where the seesaw is balanced on. Okay? Now let us look at that. When him have a weight, W, and weight is measured in Newton, no so, which means that weight is also a force. Weight is also what? A force. It is a force. If you never know, let me tell you. Over here also, him, little head, also have a weight. Him weight is measured in Newton. So I didn't tell you when you go to market all these years, but weight measured in a pound and kilogram. Not no go so. The original unit for weight is the Newton. It's a force, and you find weight by multiplying mass times gravity, which is usually 10 Newton per kilogram, or you can say 9.81 per kilogram. But CXE love to use 10. Okay, so weight is measured in Newton, which is also a force. So, oh good, so when you see a weight, a force will go under, so you understand? So little head is at a certain distance away from the pivot, and big head is a certain distance away from the pivot, and each of them are exercise a force there and a force there. Now you see, by the time you multiply, if you must multiply film weight by the distance that is away, which is different, and film weight all the way bigger times the distance that away from the pivot, which is also different, then you find out, say, the seesaw balance. You understand? Because what? The anti-clockwise movement, which is the principal movement, which is what I will go into, because the clockwise movement is going to be equal to, I remember say movements is equal to Newton, which is the force times the distance. Okay, so we're going to have some calculation. You will actually get back the same movement over here. Okay, that is why it balances. You cannot have equilibrium or balancing without the the clockwise movement being equal to the anti-clockwise movement. You must understand that. So the next one, in which all I know have done in your life, a door. Door, hanging on a door jam. That's the jam right there. And between the door and the door jam is the hinge. The hinge. Everybody ever look on some hinge on the side of a door? Okay. So that is where the turning point actually happens, between the door and the door jam. Movement occurs there also. I want you to get up, and I want you to open your door, right? And I want you to put your hand right near to where the hinge is on the door. I want you to half open the door. I want you to put your hand right on the door, not between the hinge and the jam, right on the door, and try to push that door open or to push it close. Put your hand right near the right on the door. Don't put your fingers in between the door and the door jam for you crush. Put your hand right on the face of the door that is near to the hinge and try to push the door open or to try to push it close. I guarantee that you will not be able to do it. Or if you even do it, it will be very, very hard. But you take your hand now and put way out to the other end of the door. Hold on to the other end of the door and turn the door, and you will see that the door turns very easily. Why is that happening? Moments is happening there. Whenever a turning point is affected upon a certain distance away by a force from it, then moments will come into consideration. And the amount of energy where that take you for you push the door when your hand is near to the jam on the door is going to be a lot less and a lot harder than you can manifest than when you put your hand way out. The distance away that you increase and the amount of force you apply to the door to push it or close it, that distance away from the pivot actually allows a lot more force to be put in upon the material and the door close easier. So those are three beautiful ones. There's a lot more applications, like when you use a crowbar. Why man have to use crowbar to dig down one door instead of you try to use them bare hands, right? Moment this again. The crowbar long, them apply a distance, a force pan at a certain distance away from the turning point, which is at the tip of the crowbar, and so the wood fly up. Another one also is, why do you use a tweezer to pluck out a hair out of your nose or an eyelash rather than using your finger? Why your finger can't do it as good as the tweezer? The tweezer allows you to put it the force a good little distance away from where the hair is that you want to pluck out, and you therefore taking less amount of force to basically pluck it out. Why do you use a hammer to pull up a nail and you can't know what the nail in the board and you can't take your hand take it out? But if you go there with a hammer and put the hammer right on the nail, the claw of the hammer on the thing, and the nail, right? Claw of the hammer right round it, right? And you basically put force down on it, basically the nail lifts up. and that distance that is between your hand and the claw of the hammer that holds the nail is the great benefit that allows you to actually take up that nail with less force, which your hand could not manifest, because the distance multiply the force by the little bit of force that you put in at the hammer now by a lot. Even when you go to the nail and try to pull it out, you put in more force, yes, but you can't do it because your hand cannot manifest that much force. But when you go away from it, the distance start multiply the little drop of force that you were using before holding the nail and increases it a lot. Got me? Right. So let us now look at something called the principle of moments. And this is something that you must memorize. You have to memorize it and you have to appreciate it. Now, this principle states the following. For a system in equilibrium, or for a system that is balanced, the sum of clockwise moments is equal to the sum of anti-clockwise moments. Sound big and bad, not true, but it is not big and bad. Clockwise moments is equal to anti-clockwise moments. That is the principle for moments. When a system is balanced, alright? So if the system no balance, if you can't balance the system or the body, then that means that it is not in equilibrium. Therefore, the clockwise moments is not equal to the anti-clockwise moments. Alright, so let us define anti-clockwise moments and clockwise moments now. Right, guys, so let's look at anti-clockwise moment and anti-clockwise moments and anti-clockwise moments. Right, so having looked into the principle of moments and understanding that for a system to be in equilibrium or balance or a balanced state, then the sum of clockwise moments must be equal to the sum of anti-clockwise moments. Now, so that was the principle of moments, which you have to memorize. Now let us define what is clockwise moments and anti-clockwise moments. It is very easy. It's not hard, just sound big. So the clockwise moments is a moment that tends to rotate a system in a clockwise direction. In a clockwise direction. What do I mean by that? You see this clock right here? You see the direction it is rotating in? Towards the right? That is called the clockwise direction. If you know how a clock rotates around its dial, then you automatically know a clockwise direction. Also, alright. The opposite of the clockwise direction is the anti-clockwise direction. Okay? So now let's see. The anti-clockwise direction is the direct opposite of the clockwise direction. A moment that tends to rotate a system in an anti-clockwise direction. That is the anti-clockwise moment. The anti-clockwise moment, which is the opposite of the clockwise moment, is a moment that tends to rotate a system in an anti-clockwise direction. Now what do I mean by all of this anti-clockwise and clockwise direction? If the clockwise direction is what it is, then it will rotate to the right. Right? The anti-clockwise direction would go opposite, and you would see the hands of this little dial going round and round in the opposite direction towards the left. Okay, so that the clockwise direction is that way, The anti-clockwise direction is that way. Okay, so that's a wonderful analogy. Let us look on this as it refers to the lever. So the principle of moment that I just told you about, it has a different name. It is also called the principle of levers. And I'm sure that everyone around in the lab would have used the beam balance. Okay? And would have shifted the little dials on the beam dial, the little weights on the beam dial, until you guys got your little line to be datum line and the beam balance to be line. Two of them line up together. Remember when you guys were measuring your stone and your metal blocks with the beam balance, you have to shift the weights span so that it basically the two line them meet and even and equal and stable and move. Alright, good. That was utilizing moments as well. If I didn't tell you at the time, now I'm telling you. Okay? So the lever principle is also called the principle of moments. Because how a lever works, and you can look on YouTube on how a lever operates and what it is. Okay, so if you don't know what a lever is, go and look it up, right? So this right here is the seesaw, right? The principle of moments is right here. In the previous questions, we see that we only had one force, not true? One force. So them the maths very easy, quick and fast. No problem to find out the moments. So. But now, you basically have two forces. The two forces you have now. So now the maths get a little bit more challenging. And you would have had to know how to do algebra to know how to do these kind of maths that we're going into right now, which is easy, and I'll break it down. So force 1 is there, force 2 is there. Over here would be the clockwise. The clock over here, when you basically calculate that force times that distance right there, that would give you the clockwise moments, okay? And it would tend to turn the thing in that direction. Now over here where you have force 2, you would multiply it by the distance from there to there from the pivot to that, right? And that would give you the anti-clockwise moments. The same calculation that I gave you a while ago, are the same calculation we find the clockwise moment and the anti-clockwise moment. The anti-clockwise moment would therefore turn the thing in that direction. Do you see what's going on here? So one goes round to that direction, one goes down to that direction, to the left. Okay? And that is where we'll be looking on some calculations right now. Right. So, the machine that is used to measure the Newton, which is the force, is called the Newton meter. So whenever we go into the lab and we're going to do a CXC lab based on this moment of a force business, and we'll be doing an experiment, the machine that we'll be using to measure the newtons or the force that being applying, right, from a certain perpendicular distance that we can actually find the moments, that machine is called the Newton meter. The Newton what? Newton meter. Just like it is the same name as the unit of moments. Okay, it's the Newton meter. Alright, so we would have put our little force, measure the force that is being applied, right, from a certain point. Okay, and then now we would basically measure the distance with our ruler away. Alright, so we ruler here. And then basically we have the force. If we know the force, then we know the distance, right, say a 5 centimeter. Then we can basically calculate, we'll say 8 Newton there, so then we can basically calculate the Newton, the moments, also by multiplying the 8 times the 5 in the laboratory setting. Wonderful. Right, so now we're going into the fun part of stuff. Right, now we're going into the calculation. Now I'm going to start off very simply, and then we go into some more complex stuff. Okay, so the first thing you need to identify what is the equation for the moment of a force. The moment of a force equation. Now the moment of a force is simply found by multiplying force, which is also going to be newtons, times distance in meters. You may see questions where centimeter is given to you in the distance. If the question does not require you to convert the centimeter, just work. Okay? No, in this question it does. Alright, the question says, and I have drawn up my diagram, we have a door here that is hinged on a door jamb. Okay? The question says the distance from the hinge to the handle on the door is 70 centimeter. If the handle is pushed with a force of 8 Newton perpendicular to the moment of the force, or 90 degrees away from the force, you have to incorporate that in the equation. Okay, them just tell us say perpendicular. So you sure say the moment equation can work. Okay? Calculate the turning force, calculate the moment of the force turning the door. That them want. Them want to calculate moments. Okay? Quite easy. You have distance, you have force. You hear say it is perpendicular away from the hinge or the pivot. So you know most don't say a moment you're going to use, guys. So let's go. So first things first, let us convert the centimeter to meter. So therefore we have what? 70 divided by 100. Can you know say 100 centimeter make a meter? No, so equals 0.7 meter. But therefore now we can run through and calculate the more calculate. Right? Therefore 0.7 and you put in a unit meter times 8 Newton is equal to 5.6 Newton meter. Right. So the reason why the meters and the newtons cannot cancel out is because they are different. Therefore, plus you're multiplying their magnitudes. So you end up with the Newton meter. You see why you end up with the Newton meter? You did not end up with Newton per meter because they never divide them. It is not force divided by distance. You would have got Newton per meter. It is force times distance, hence you get Newton meter. Wonderful. Guys. Now in this question, we basically have a different setup but are the same thing. Okay? We have a different setup but it is the same thing. Now this that you're seeing right here is called a bicycle axle. A bicycle axle. Everybody know that on a bicycle, you know the chain run pony, you understand? And it actually with those jagged edges actually grip the chain and make things move, right? And the axle is connected to the pedal. And what connects them both is called the crank. Alright, it's called the crank. Alright. Now the question says the crank of a bicycle pedal is 16 centimeter. 16 what? Centimeter long. And the downward push of a foot, meaning so the downward push of a foot, that basically occurs right here where the foot go and put force on the bicycle pedal is pushing a force of 400 newtons. Right? Calculate the moment of the push of the foot when the crank is horizontal or upon a straight. When the crank of the bicycle pedal is horizontal, its length is perpendicular to the downward foot push. So the perpendicular distance D from the pivot to the line of action is the 16 centimeter. Okay? Right. So we have our distance here. Right there. So we distant of 16. Right? Because the crank from the pedal to the foot go at 16 or so. Good. And then now the force a come down so on the foot. So watch here. Watch you catch. See what the perpendicular thing are coming now. Bop. Bop. You understand? See the distance there from the point turning up from the turning point, which is the pivot right here. You see the turning are going also. And you take your foot now, putting down force on the pedal. That is where you get your 90-degree angle. And that is where the perpendicular business come in. So you know say you can't just run out and go just basically say, oh, my foot push 400 newtons on it, therefore 400 newtons is basically going to reach the axle. No. There is a turning effect because the force is actually being incorporated at a 90-degree angle. And that is what the beauty of what we want to get of that thing called perpendicular and how it obviously have to do with force. You don't have to use no angle in the calculation, you just have to appreciate it, okay? Therefore, now I can go run through and calculate my moments now. Right? So therefore, moments is still force times distance. Never change yet. Alright? But me have my thing now 16 and because I want to teach it, if you want to appreciate the conversion more, I'm going to do the conversion other one as well. So 16 divided by 100 because 16 centimeters converted to 1 meter. You have to use a conversion factor that 100 centimeters make a meter. So 16 into divided by 100 is equal to 0.16 meter. Okay? Now let us go and do some calculations. So therefore now, force is 400 Newton, right? Times the 0.16, right? Therefore the moments is equal to 64 Newton meter. You can do that on a calculator. Alright, see if sir is wrong. 64 Newton meter. Newton times meter. Newton meter. Alright, 400 times 0.6, 64. Okay, so that is another very good question which I like. And this one shows how the 90-degree angle comes in. And it was also 90 degrees on the door, but I did not show that one. Okay? Alright guys, so having looked on the principle of moments, which is that the sum of anti-clockwise moments must be equal to the sum of clockwise moments, we can go into some more high-end questions, okay, which is a simple approach still, right, as you would have seen if you checked it out the past papers. Alright, so in this setup we have a lever. Alright, lever looks or operates just like the seesaw. You see something like this, you may see somebody on it, you may not, you may see two weights. Alright, two slotted weights that you must have seen in the lab at either sides. Those are called slotted weights, okay. In that case this is now a lever, not a seesaw again. Alright, so in this question, question number 1, we see that we are asked to find the distance of the 4 Newton weight away from the pivot. So there's the pivot right there. We have a 4 Newton weight. We don't know the distance that it is away from the pivot, right? But we have a 5 Newton weight also, and we know that its distance away from the pivot is 0.2 meters. 0.2 meters. We are asked to find the distance of the 4 Newton weight. In question number 2, we are asked what forces are acting on the lever to keep it balanced and state their directions, which is something we really want to understand. Alright, so let us go into calculating it. First, we state the principle. Let me see, we can put a little space here for calculation. Alright, you know, so this is 5. Alright, now we'll calculate now this box. So we state with principle. Anti-clockwise moment is equal to clockwise, or sum of anti-clockwise moment is equal to the sum of clockwise moments. You must understand that first. Alright, so we know that over here, because that is this 4 Newton weight is going to pull it down in that direction, then therefore this is going to be the clockwise side. Alright, so it will pull it down that direction, therefore clockwise. And that is so over here to the left will be the anti-clockwise moment. Alright, so how do we find them? How do we calculate the clockwise and the anti-clockwise moment? And if even when we do that, how am I going to find the distance of the one? Not complex at all. So let's see how we go about this now. Alright, so let's do that. Okay, don't want to erase the diagram. So we know that to find moment, when we did do it over in the simpler questions, to find a moment about a point, that's what we were doing. We only had one force, but now we have two forces, 4 Newton and 5 Newton. You're going to end up with sometimes you have all 3 forces. Okay, we'll work some questions like that too. Alright, so when you do that, you understand, say, oh, this is nothing hard. It's just the same equation of finding a moment, which is, and you don't know finding moment is equal to force times distance. No, so force times distance. You don't know that. So you basically state force times distance is equal to force times distance. You understand what I'm going? Force times distance, force 5 Newton times 0.2 is equal, which is the anti-clockwise moment, is equal to force again times distance, which is my unknown. Okay, which is my unknown variable. Alright, so force times distance is equal to force times distance. So if we find the anti-clockwise moment and we find the clockwise moment, is the same equation. Okay, it's just that you are putting them side by side and I'm going to do some substitution. Okay, you must also appreciate the fact, moreover, that the force times distance equation is the same little moment equation that we give you from first. No change. Alright, so let's do that now. Since as you know, say force times distance is equal to force times distance, which to find the clockwise and anti-clockwise moments, let us do that. Okay, so how do we do that? So we know, say 5 times, you keep the things together. You can't come over here and give the 4 to the 0.2 when the 0.2, look where the arrow is pointing from the point of action of where the 5 Newton is acting to the pivot. Therefore, you know the 5 Newton belongs to the 0.2. Not the 4 Newtons distance belong to that up, so we unknown. So you say 5 times, and you put in a unit them, always put in a unit, 5 Newtons times 0.2 meter is equal to 4 Newton times x, because x is what we'll be finding for our unknown distance. Alright, so how me do now? First things first, me get to a reader where me can get reader. Over here me have everything we want, so me can say 5 times 0.2, and 5 times 0.2 is what, guys? What is 5 times 0.2? That is 1 Newton meter. So all of this get rid of this. So 5 Newton times 0.2 meter is 5 Newton meter, and this is equal to still 4 Newton times x. Now, how do I possibly find x? You guys out there, you are in grade 10 now, going to go into grade 11, you should know how to substitute a simple algebraic equation like this. So you ask yourself the question, what is the 4 doing to the x? Obviously the 4 is multiplying the x. So to get rid of 4, I have to divide it. No so? Yeah man. And that 4 cancels out. And you know, whatever I do on the left, whatever I do on the right, I'm going to come over and do on the left. Is that right? And look at that. So what does that do? That this right here, the 4 them get cancelled out. Right? Therefore, right? So x is equal to 4 Newton divided by 1. No, so 4 divided into 1 Newton meter. The Newton meter cancels, the Newton cancels the Newton, and as we know, 4 into 1 is equal to 0.25. What? And because the 4 Newton cancel the Newton in the Newton meter, I get back my meter. So therefore 0.25 meter is equal to x. Alright. So right here would be then 0.25 meter. Now, since as you see that, you have to understand something very, 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 very good, dear children. When you go see now, I will show you, say, the anti-clockwise, the clockwise movements over here is equal to the anti-clockwise movements over here. How do I prove that the principle of movements actually works here? Now, number one, the reason why I didn't know, say, I could have used the principle of movements here is because of the fact that no, the thing was balanced. The question stated that it was already balanced. Okay, so me know say it was in equilibrium already. That's a good thing that you should note as well. Alright, now let us prove that it is actually that anti-clockwise movements is indeed equal to clockwise movements, therefore proving the principle of movements in this question. So we say 5 times 0.2, right, is equal to what that equal to? 5 times 0.2. is equal to 1 Newton meter. That's all. 4 times 0.25. What is 4 times 0.25 equal to? Also equal to 1. Right? So you are seeing there that anti-clockwise movements is indeed anti-clockwise movement on the left is equal to the clockwise movements on the right, because the 5 times 0.2 is equal to 1 Newton meter same way, and the 4 Newton, which is though it is a different force, because it is being multiplied by a distance that is 0.25, it is going to give me back 1. So you see the principle of moments is obeyed in this question. Now let's look at the second question. It's a very good question as well, which I want you to understand. Now what does it say? What forces was erased? What forces are acting on the lever to keep it balanced and state their direction? Alright, now number one. Let's see if we can get back the diagram. Alright. Now, three forces is acting on this thing to keep it balanced, guys. Three forces is acting on this thing to keep it balanced. The first force that is acting in it is the 4 Newton weight. 4 Newton weight are, so weight is actually a force, right? So, first force, 4 Newton weight. And the direction that it is acting is what? What do you think the direction that it is acting in? It is acting in a downward direction. Although it is acting, you could also say it's acting in an anti-clockwise direction, right? That would be good as well. Okay, so downward. Downward or clockwise. Alright? CX in a kilo. Okay, the second one is obviously the 5 Newton weight or the 5 Newton force. 5 Newton force here. Force or weight can go interchangeably, same thing. Right? 5 Newton force, and it is also acting in a downward direction. Can I act upward, guys, or you could say it's anti-clockwise, to be precise. Right? Cannot say it's going left. You can't say it's a go down. You can't say it's a go up rather, because gravity is going to act on that mass in a downward direction. So even though it's going in an anti-clockwise direction, right, it's still acting downwards because gravity causes everything to fall. You must appreciate that fact. Alright, and part 3, and the third one now, which really and truly you would not see if you never did read about or study when we did teach you before school lack about normal force. Normal force is this. Go back and check your book. You see when an object is placed on any other object, right? And that object which is placed on the object, see table here, see block them put on the table. The weight of this, which is a force, acts down on the surface of this. Okay? And you know what the surface of that do? Him say, well, I'm not take that. So, I'm giving you everything that you give back, that you gave to me. And he basically pushes on the object with the same force that the object is pushing at him. So if him push down with a force of 5 Newton, the table, will also push back up with a force of 5 Newton, and that is called the normal force. Now when you study the diagram, you see that the bar here, the lever bar, is actually rested on the pivot. What do you think the pivot is going to do? Just take it so? No. He's going to put back, so everything here, so the weight of the bar combined with the 5 Newton force, yes, and the 4 Newton forces, so all of that force, if you can imagine, rest on this pivot right here, and the pivot say, I am giving you back the same total force you give me back. So the total force that will be opposite and would be anti-parallel, right? These 5 Newton and the 4 Newton would be parallel. Parallel means they are in the same line, okay? They are in the same line. But the normal force and the total force of them, they are basically vertical to each other, right? But is still considered a normal force, because the normal force actually always acts in a vertical manner. Alright? So the other one is normal force. A normal force is acting in an upward direction. Upward direction, guys. Okay, wonderful. So that is that for that question. Alright, guys. So let's look at a question like this. Now we are stepping up the ante. Alright, I'm getting more technical. So in the first question, you have seen where only 2 weights were acting on either side of the lever. So, but suppose you had 3 weights or 3 forces acting on that lever. How would you deal with the question? Well, in this question, we have a similar setup. We have a situation just like that. We have 3 different persons sitting on one seesaw. Don't act frightened, because I know all of you all have done that. 3 or 4 or 5 and 10 on the basic school on one seesaw. Don't act frightened. Right? So we have person A, we have person B, and we have person C. Alright? It's not hard. You just take some substitution and some addition. Okay? So the same principle also. Is it balanced? Is it balanced? Yes, it is balanced. Therefore, this seesaw is in equilibrium. Okay? Therefore, the principle of moments can be utilized. Alright? So, let us take some things into consideration. How do I treat this? Do I still use the same anti-clockwise movements is equal to clockwise movements? Do I still use that? The answer is yes. But you're asking yourself now, sir, how may I go do that when a 3 force me have, sir? As a matter of fact, you want me to find one of the forces unknown, sir. Me have 3, them want me to end up with 3 forces, sir, and them give me also 3 different distances, sir, for each of the person them. How am I going to work this out? It is quite simple. When I introduced to you the principle of moments, I told you that it stated that the total anti-clockwise movement is equal to the total clockwise movements. Okay? That word total, they show you something, say, it can be any amount of force that act on the right hand side. Right? And it can be any amount of force that act on the left hand side. You can utilize them you can utilize all of them or some of them to basically find out anything that you want to find out. Alright? So, how do we approach this question? Let us see if we can approach it. I'm sure I do not need to state back the moments principle or the moment equation. But for some of you, what do it? Show you that may I use. Alright, so the moment principle is that anti-clockwise movements equal clockwise movements. Also, anti-clockwise equal to clockwise. Also, alright, our total anti-clockwise equal total clockwise. Alright, over here, over on the left, person A, we want to find his weight. We already know the weight of person B to be 3 Newton, the weight of person C to be 2 Newton. Alright, so first thing we have to ask ourselves, how many ask out the equation? Quite simple. Same force and distance again. You know, say him, person A, is the anti-clockwise distance, because his weight is going to turn that way. Person B and C total their moments together. He has a weight that is 3 Newton and he also has a distance. Therefore, I can calculate a weight for him. He also has a weight which is 2 Newton, right, or a force. You know, say weight and force, I see him. I go continually say that. Alright, he has a 2 Newton weight or a 2 Newton force acting on the seesaw as well. And he has a distance that is 1.8 meters, right? So, me can find free moment too. And when I find the moment for person B and the moment for person C, I can add them up and have a total what? A total clockwise moments. You understand where I come from? Alright, let me see me can that now. And if I do that, I can find then the unknown weight for person A utilizing his distance as well. So let us see if we can attempt that. Alright, so that is then now 3 times, or 3 meter, put in units, 3 meter, which is the distance of which person A is actually acting from the pivot, right? 3 meter, I'm going to make the weight, the unknown, times x, right? So that a force times distance or d, so that F times d, you know, see it, alright, good, is equal to the anti-clockwise moments of person B, which is 0.5 meter times 3 Newton, right? Good. Let me bracket that, always bracket it, plus, because the two of them is not on the same side, and the two of them also is going to be the clockwise movement. When we finally add up them different movement there, the two of them are going to have a final clockwise, total clockwise movement. So, plus the 1.8 meter that person C is from, 1.8 meter times 2 Newton, right? So in each case I use force times distance here, force times distance there, right? Force that are x Newton times the meter, and force times distance again. So same principle may I use. So let me do over here first. It's always good to do the side of the equation where everything you know, but no unknown upon it. Deal with the unknown last. So over here, 0.5 times 3 is going to equate you to 1.5 Newton meter, yes or no? So, and then now, plus 1.8 meter times 2 Newton is equal to what? What is that equal to? That is equal to 3.6 Newton meter. 3.6 Newton meter. Alright, when we add up all of them there, two of them there, what do I get? I get 5.1 Newton meter. So 5.1 Newton meter is still equal to 3 meters times x, which is the weight we want to find, x newtons. So I ask myself the question, to make x the subject of the formula, what do I do? Me have 5.1 Newton meter over this, so, right? When we add up those, and I have x over here multiplied by 3. What do I do to make x the subject of the formula? I simply divide by 3. That cancels that, and if I do it on the left, I come and do it on the right. Alright? Divide by 3 meter. And what do you think happens? The meter cancels the meters first, you see? And that 3 now into 5.1 Newton is equal to 1.7 Newton. So easy, guys. So it's all about addition and what do you call that thing, you know? Substitution. Right? So when you know how to set up a thing, when you know say a 3 person you have, guys, are 3 different weights, 2 different weights per one side, whatever you have you can work with it. Okay? Now, therefore, his thing right here would be 1.7 Newton. 1.7 Newton. Okay? So that would be person A's weight. Quite easy. All you need to know is look over here and say, oh, two of them on the same side. Then that means me have to go add up them. You understand? Me have a weight for him, me have a force for him, me have a distance for him, me have a force for him, which is the weight of him also. And me have a distance for him, therefore me can find a moment for him and a moment for him. Add up the two moments and then get a total clockwise movement, which is acting in that direction. And we have a total clockwise movement, anti-clockwise movement over here also, because of him one over there, right? And also because there is a distance for him away from the pivot and a unknown weight for him, which is what I found. If I had known this and I had basically I did not know that, I could still work it out with all of the other things to find that. If me did have everything for him and I did not have the 0.5 meter for him distance for him, I know it for him also. I could have worked it anyway I want to work it and find it. Okay, guys, just telling you that. Alright, guys, so let's look at two different questions. Now I say to you that these principle of moment questions can come in any way, shape or form, and they may throw you off guard when you first see them, but do not be dismayed, it is the same thing. Okay? So in the question number 1 here, I'm going to do question number 2 too. Okay? So we're looking at these questions now. We see question number 1 gives you a case where, similar to the first question that I had worked, right, with the wrench or spanner, turning on a nut, right? But the difference with this question and the very first question that I did is that, and you can see it, this spanner have two different forces acting on it. Two different what? Two different forces acting on it, right? We have a force acting here of 100 newtons, which is 0.25 meters away from the pivot, which is the turning point right there where the nut is, right? And we have another force 180 newton that is at a distance away from the pivot, which is the nut that we do not know and which we will want to find. how do we find this? Why look so technical? How me I go do it? You say to yourself, it is not hard at all. You have to understand that once you see two force, and once you get two distance, even when one unknown, then basically at the same principle of moments thing is coming out, guys. It is no different. It is not hard. It is something that you can do. So, do you have two forces, you say to yourself? Yes. Or do you have two distances? Or even though one is needed to find, do you have two? Or will you end up with two? Yes. Therefore, and even for the 3 or 4 or 5, it didn't really matter. We could have still do it, right? So, a moments we do. Okay, so we say anticlockwise moments is equal to anticlockwise moments, right? So therefore, this one that is to the left, it will be good. You could have put either of them as anticlockwise or clockwise. So the maths would have worked out the same if you check it out. You understand? So, but let us arrange them. The maths will never work out the same if you do not link them with their correct distance. Alright? So you see that the 180 goes with the unknown distance and the 100 Newton goes with the 0.25 distance. Okay? So let's arrange that. So we say force times distance is equal to force times distance. So F times D is equal to F times D. So anticlockwise moment, I know that force times distance is moments. So is equal to the clockwise moment, which is also again force times distance. Alright? Let me erase that for space. Therefore 100 newtons, which is the force, times 0.25. Therefore 100 newton. Can I get more space here? Let me see if I can do it at the very top. Alright, I'm going to see if I can do it at the top. So then, force times distance is equal to force times distance. Okay, so that is what now? 100 Newton times 0.25 meter is equal to 180 Newton times x distance, which is what I want to find. Okay, so let's, guys, what would you do first? Let's find out over here, because over here does not have any unknown variable. Over here is my unknown variable. Though over here will give me my clockwise distance, and over here will be my anti-clockwise distance, my anti-clockwise moments rather, and my clockwise moments, right? Because over here does not have any unknown, it is highly necessary to work over here first, even according to the rules of algebra. Alright, so 100 times 0.25 is what? 100 times 0.25 is 25 Newton meter. 25 what? Newton meter. As you would have known, that half of a 100 is 50. Therefore, quarter of 100, which is 0.25, has to be 25, right? And then I divide by 180 over here, because 180 is multiplying my x, and I want to make my x subject of the formula to find him. So 180 cancels 180, and I come over here and do the same thing again. 25 into 180, right? 25 divided into 180, or by 180. The 180 Newton cancels the 25 Newton, and then the 180 divided into 25 is equal to 0.1 meter. 0.1 what? Meter. Therefore, the distance away from the pivot that this 180 Newton force is acting is 0.1. Not hard, is it? Not hard at all. Let us look on another high order skills question. Right here, we are given a setup. We are given a what? A setup. We are given a case where we have a girl that has a weight of 150 newtons. 150 newtons. She is 0.25 meters away from the pivot. 0.25 meters away from the pivot. Now, a guy comes along, one of her friends, right? And he is weighed in at a force of 250 newton. Now he wants to know, how will I possibly be able to get this girl to be balanced on this, for me and her to be balanced on this seesaw, right? Should I sit at 1 meters away from the pivot? Should I at A position? Should I sit at B position, which is 1.5 meters away from the pivot? Or should I sit at C position, that is 0.5 meters away from the pivot? What do I do? How do you approach this question, guys? First things first, it is quite easy. Alright, let me erase the top part first. I need a lot of space. You know that the principle of movement says that anti-clockwise movements has to be equal to clockwise movements. So any one of those moments, any one of those distances, that when you multiply them by the weight of this guy right here is equal, and you get a moment that is equivalent to her moment, then you will be good. So we say anti-clockwise moments equal clockwise moments, right? Which is force times distance is equal to force times distance, because force times distance is the equation for a moment, whether I'm clockwise or anti-clockwise, and it is the same thing for that over there, right? So her anti-clockwise, her distance is 0.25 and her force is 150 Newton. So 150 times 0.25, right? If I follow this through, right, I mean, I do not yet, I'm not touch it yet, okay? Because me know say the weight over here saw 250 Newton, right? But them really are try to ask you, if you find the distance, check it out. Them want you to find the distance. That's all them want you to do. Them want you to find a distance. Is it 1.1 meter, 1.5 or 0.15? That when you multiply it back, you're supposed to get the same thing from both sides. So let us check. 150 times 0.25. How much? Let us find her moments. 150 times 0.25. Let me see if I can calculate that rather easily. $37.5. Alright, so her moment, her total moment over here is 37.5 Newton meter, which is equal to cm250 Newton times x, right? Which is a distance that we do not know. How do we find this? Simple. Divide it by 250. That cancels that. Newton cancels Newton. Come over here, do the same thing. 250 Newton, that cancels that, right? 250 into 37.5, right, is equal to, let's see, alright, so 250 divided into 37.5 is, I need space, let me put it here, is equal to 0.15 meter. 0.15 what? Meter. Okay, so that is not saying that he should sit at C position. Can we prove this though? Can we prove this? Yes man, let us prove it. First things first, we know that moments, anti-clockwise movement, have equal to clockwise movement. That means they can't be different. No, so, alright. We know then, after we set up the equation, that 0.25 times 150, if we find fear moment that she is acting on out here, we found it to be, what did we find it to be? We found that her moments was equal to 37.5, no, so, Newton meter. Then that's supposed to equal to the same moment over here, so, and we find the distance over there, so equal to be 0.15 meter. So let us see if it's 0.15 meter, which is the distance of C's position. Let us see if it equals to 37.5. Because if it does not equal to 37.5, then it cannot basically agree with the principle of moments. So definitely it is equal to 37.5 Newton meter. Alright, so therefore that's how you would approach a question like that. You just have to think outside of the box. Wonderful. Alright guys, so let's look at this question. Right, we see this question is very looks very different, not true? Right, we see that within this question we see a rod, right, a uniform rod, and we see this thing here. Now this thing would catch you off guard and you would be saying, what is that? Where pivot, the way all that little triangles you usually draw like both yaso and say that a pivot, where all it gone? Right, you know it's no pivot yaso. Well guys, this is the pivot. In this question, the rod is suspended from above, right? Obviously you guys have gone into rooms and you have seen crystal chandeliers hanging up from the roof, right? Well, right from where the ceiling is to where this chandelier is actually, or the tension wire is actually screwed into the rod. That is where the point of action turns. If you ever look up in a ceiling and see a fan really and truly spinning, and the rod will hold the fan to the roof, swirl a little bit, that right there is the action and turning point. So right here would be your pivot. Okay, you in a moment's question you're always giving your pivot, even if it does not always look like this, right? Remember in the question that was given to you with the spanner, right? It did not look like that. It was the nut. You have to use your common sense to determine where the turning point is. Like just like in the door one, right there at where the door turns and the hinge, that is the pivot. Right where the hammer pulls up the nail, right there at the claw of the hammer, that would be the point of action, the turning point of action, right? So you must be able to utilize your common sense and your imagination. That's why you can't really teach physics a lot, especially in this kind of part of the syllabus, without diagrams. Alright, so this question is different. Why do I say so? You see, in this question the pivot is not in line with the center of gravity. What is Sir saying when he says that? You see in all of the previous question, like the seesaw one and everything else, the center of gravity was always in line with the pivot. You get where I come from? Okay, and you would have had a force there and a force there, right? But in this question it is different. Okay, why is it different? Is it hard to find out? No, it's not hard to find out, but you must be able to define what the center of gravity is before you do this question. So let us define, and I want you to write down what the center of gravity is. Right, center of gravity, otherwise called COG. Alright, center shortened for COG. Center of gravity, point in which all of on which gravity acts on the total mass of the object. Alright, so you have that definition. You can pause the video and write it off. I'm going to erase it. Point in which gravity acts on the total mass of the object can also be defined as such. The point in which all of the weight of the object X. So you can use either one. What's that? So the center of gravity is the point in which all of the weight of the object acts. You can use anyone you want to use. Okay, I like this one which incorporates the term or the name weight. Alright, and what do you know about weight? What do you know about weight? You know that weight is a force. No, so, and therefore it is measured in Newton. That should be telling you something. That should be telling you something. Okay? Alright, now. So let's look at the question once more again. Right? Looking at the question. You see that the center of gravity, right, is not in line. You see how this look equal? Between theirs and the center of gravity upon a regular shaped object like this is halfway. Right halfway in the middle of the object. Upon a regular shaped object like this. This is not an irregularly shaped object. It's a rectangle. It's a rod, but it's a rectangularly shaped rod. Okay? Center of gravity would be right there in the middle. And common sense would tell you that the engineers would put the pivot right in line with the center of gravity. Okay? So that's how I said a normal question that we have been looked at. Now we never have to take center of gravity in a consideration when we are basically doing the question. But over in this question now, you see the center of gravity, look how long the rod be. You see that the pivot is not in line with the center of gravity because the center of gravity is at A according to the question. Right? If the weight of the rod is 1 Newton, that acts at A. Here is A, that point right there, which is the center of gravity. And it is 20 meters away from the pivot. It is not in line with the pivot like in this one. If you check out all of the questions that we have done, the center of gravity was never mentioned because it was right in line with the center of with the pivot, and it would have cancelled out. They would have cancelled out. But over here, if the center of gravity is mentioned in the question and it is not in line with the pivot, it never is when it is included in the question, right? You have to understand, say you need to take that weight of the rod, right? Or even if they ask you to find the weight of the rod or the mass of the rod, you must take the center of gravity into consideration and treat it as the weight. And treat the weight as a force. And remember that the weight acts at the center of gravity. Where does the weight act? Right at the center of gravity. If I should take you up and I should measure you and find the center of gravity, I could determine that right there is where all of your weight is acting. And if all of your weight act there, that means the total force of your body acts at that center of gravity. Okay? You must understand that and you must appreciate that. Okay? Now, right? Let us see if we can do this question. So I want you to take consideration that the center of gravity, where A is where the total weight of the object is. And we know that the total weight of the object is 1 Newton. Therefore, I can put 1 Newton here then. No so. I mean, we say anyway the center of gravity there, and that's the total weight act. No so. Therefore, I can put 1 Newton here. No so. And I know that 1 Newton force, which is what weight is measured in Newton, is 20 meters away from the pivot. Therefore, I can calculate a moment about that 1 Newton force. Okay? So when you hear about weight is included and I'm going to tell you the weight is X distance away from the pivot, you can calculate a moment about that weight by simply multiplying the weight times the distance. Okay, and the weight is always given in newtons. Alright, so the question says, what must the weight of block 1, and block 1 is right here, of block 1 be for the rod to be level if the weight of the rod is 1 Newton that acts at A? Alright, so it's a simple question, and we're going to be using the same kind of equation that we would have been using before, but it's gonna be a little bit different. We're gonna have to do some stuff that I had taught you in the past first before you come here. I had taught you how to calculate weight. I had taught you how to convert. All of that is needed in this question. Okay? All of that is needed in this question. Now let us observe the question. We know that block A has a weight, where them want to find. So, which is also a force, where them want, which is a force, right? So them want to know the force we act as up. Alright? And they know that the weight of a block, which is a force, is 10 meters away. So that means we can calculate, if we have a force, I have a distance. So. Therefore, I can calculate a moment right there. No, so. Right? Obviously. And the distance there is 10, and the force there is unknown. I can calculate a force, the moments there. So therefore, I can use the clockwise, anti-clockwise principle, or which is also called the principle of levers, to really and truly do this question. Over here, me have a case where them tell me say a 20-gram block, which is block 2, is at the end, right? And we see that the center of gravity is also, not always, my apology, is in this case also on the same side. So over here so would have been anti-clockwise, as you might have guessed, and over here would have been the clockwise moments. But the center of gravity is also on the same side as the clockwise moments. Therefore, I can add them up. If I find the moment that is about the weight, which is 1 Newton, then I can add it to the moment that I can find for this block, which is 20 gram, which is 20 gram. Find the moment for the 20 gram block, right? When it is 50 meters away from the pivot. Now the question is, when we are going to do with 20 gram, can I just use 20 gram like that? I thought that you should have asked the question. I thought that Sir taught me that to calculate moment about an object, I need to have force, not mass. So what am I going to do? It is very easy. It's a two-step approach, but it's very easy. Take a little conversion, and it also takes a little calculation of weight. So first things first, we need to take this and move it to force. How do you take mass and move to force? Can it be done? Yes, it can be done. So let's see. First things first, we know that, let us put down the weight triangle. We know that weight is equal to mass in kilogram, right? No, so, right, times gravity, which is 10 Newton per kilogram. No, so 10 Newton per kg. So if we have this triangle right here, we can determine if we cover weight, if we should cover weight, we should see, are you seeing it? We should see, if we should cover weight, we should see that weight would have been equal to mass multiplied by gravity. Therefore, mass times gravity. And you know it's the same thing, like the force equation. Force is also equal to mass times gravity. Did you know that? Right? Force can also be equal to mass times acceleration as well. But the same thing fits because gravity can be used as an acceleration and also a force acting upon something. Alright? So that's what I'm saying to you, that weight and force is the same thing. Therefore, they have the same unit of Newton. But I now know that weight is equal to mass times gravity. Right? And weight is measured in Newton, because so for me find the weight of block 2, which is the 20 gram, right? That is mass, kilogram, gram, decigram, the whole of the milligram are all masses. They are not weights. Get that together. Mass is measured. Mass measures the amount of substance that something contains. Okay? The amount of matter that something contains. Weight is different. Weight is a product of the gravity acting upon the mass. That's why it's mass times gravity. Alright? But me find out, so me can't just go use 20 grams. right? And calculate them gravity. Everybody's supposed to know say gravity at 10. That good. We don't know say that at 10 Newton kilogram per kilogram, right? But what is the mass? I can't do that. I can't use 20 gram. I just run in so I'm going to multiply. Because gravity have a unit which is 10 Newton per kilogram. And if me have gram, me can't go calculate it, I go wrong. Therefore, I need to convert. So, 10, 20. 20 gram to kg is equal to what? What is the conversion factor of gram and kilogram? We know that kilo means 10 to the 3. No so. And if kilo means 10 to the 3, 10 times 10 times 10 is equal to 1000. No so. Right? Therefore, that is telling us that 1000 kilogram make 1 gram. Therefore, to convert from gram to kilogram, I divide. From small to large, you divide 20 into 1000. 20 into 1000 gives what? 0.02 kg. Alright? 0.02 kg, and you should check if sir is getting his maths correct. Okay, that's 0.02 kg. Am I finished there? No, I'm not finished there, because that is same mass, just different unit. That is the kilogram. Me no reach weight yet. So if me can't reach the weight of this, me can't do the calculation of moments, because me need the weight, which is going to be Newton, and then we can calculate moment, because moment equal force, which is in newtons times distance. So what me do now? Alright, can take out the triangle. You guys can replay or rewind to get it. Right? And you should have it in your books anyway. So therefore, weight equal to 0.02 times. Alright, let me do it. I'll show you even how the units come about. So weight is equal to 0.02 kg times 10 Newton per kilogram. Alright, so per means that the kilogram is actually being divided, it's divided into the 10 Newton, so it's underneath. Alright, so kilogram cancel kilogram, right? And 10 times 0.02 is what? 0.2, and me care about n because it never cancel, 0.2 Newton. Isn't that wonderful? Therefore, I now know, which as I may say is a 3-step approach, I now know that my weight here, or my force here, of my 20 gram block is 0.2 newtons. No, so 0.2 newtons. Can I go ahead and do the calculation now? Of course I can. Alright. Alright, so let's go now. So we can go ahead and write out our equation. So we know say force times distance for the anti-clockwise movement is equal to the force times distance for the clockwise movement, or the total force, total anti-clockwise movements over here is equal to the total clockwise movements over here. Okay, I say total, we mean total. Alright, but the situation is that I can get two different moments over here, which I will have to add to get a final clockwise moment. No, so as I did in the previous question. How do I get them? I repeat again. You know that the center of gravity, right, is where all of the weight is acting, and the question told you that the rod is of a weight of 1 Newton. How much weight the rod have? 1 Newton weight. Therefore, I can basically add another. Although this kind of switch up, but hopefully you understand it better. Right? Two different one. Okay? Two different force times distance, because it's going to add up to the total clockwise moment anyway. So this one is going to be for the weight of the object, and this is going to be for my 0.2 Newton 20 gram rod that we found the weight to be 0.2 Newton. Right? So over here, block 1, his weight, which is his force, is unknown. alright, times the distance, which is 10 meter, right, is equal to the center of gravity, which is center of gravity, which with its weight, where all of the weight is acting, which is 1 Newton, alright, times 20 meter, plus the 0.2 Newton there for the block, because two of them are act. You see it, one act this or one act this. Alright, 0.2 times, and it is 50 meters away from the pivot. Alright, so right here I would have 20 Newton meter, and right here I would have 10 Newton meter. Okay, 0.2 times 50 is 10. Alright, now if I add up the two of them, I will get 20 plus 10 is 30. So my total anti-clockwise movement. And even did have to do the F times D times F times D. But if you want to do it so, plus F times D plus F times D, you don't have to do it like that. But if you would like to do it like that, you can go ahead. Just know in your head, say, whenever you have two different force acting, or you can get, because you never tell you the force, but we got the force by moving from gram to force. Okay? Whenever you have them on the same side, okay, of the pivot, same side of the pivot, then you have to go use the two of them, guys. And this over here, and the two of them, on this side, are going to be the total clockwise movement. When you find the two of them, add them up. And utilize their correct distances with them. You never change up the distance to nobody. Okay? And then I basically know that over here is going to be my total anti-clockwise movement, guys. Just like in the previous question that was done in the past. Alright? So, add them up, you get 30 Newton meter. And we still have x plus 10 meter. Alright? We want to find x, which is going to be the force. What do? 10 is being multiplied rather, to the x. Therefore, if we make x the subject of the formula, I divide 10 meter, cancel him out. If I do it on that side, I come over here and do it again. 10 meter, meters cancel meter, 10 into 30 goes 3 Newton, okay? And is Newton the unit of force? Yes, it definitely is. So we end up with a 3 Newton force. Therefore, the weight of the block is 3 Newton. Alright, be blessed. Right, so let's look at this question now. So we have a rod, right? And we see that on this rod, we have a 5 Newton weight over there. We have the pivot there. And we have a 1 Newton weight there. And we have a center of gravity that is on the same side of the pivot as the 1 Newton weight, right? Both of them are on the same side of the pivot. This is on that side of the pivot by himself, right? We know that the center of gravity is the point on an object which is usually in its center, right? You see it in the center, especially for a regular shaped object. For irregularly shaped object, it's a totally different approach. Okay, we usually know that it is in the center. But you see the problem now with this question, like the previous, right, is that the pivot is not in line with center of gravity, like in these kind of questions that you were doing before. You see the pivot, center of gravity would have been so. They would have in line, and therefore they would really and truly cancel out. The force between them, the normal force, they would have cancelled out, right? But not in this case. Pivot there so. Another line there, and center of gravity the way over so. That means my gravity would have act down pondered in this direction and add to my moment that I would find here. I can find the moment for my center of gravity because weight is acting at the center of gravity. So therefore I can find a moment for my weight, which is in Newton. That's why I can find a weight for it, because we measured in Newton. And I will have to add that weight to my 1 Newton. I will have to add the moment that I calculate for the weight at the center of gravity to the moment that I will calculate for this 1 Newton force right there. Okay, so I have to take the weight into consideration, and they ask me to find the weight of the rod. Okay, so though I do not know the weight of the rod, I know something about it, that the center of gravity is actually 4 meters away from the pivot, because it is balanced already. Now they just not tell you the weight. Therefore we can use the principle of moment to solve the question. So we know that the 1 Newton weight has a force of the 1 Newton weight has a force of 1 Newton, obviously, and this is a certain distance away from the pivot. We know that the 5 Newton weight also is a certain distance of 6 meters from the pivot, and we know that the unknown weight, which is the unknown force, which is also the weight of the rod in this case, because it is where the center of gravity is, right, is 4 meters away from the pivot. Therefore, I can use the principle of moment to solve such a question. The principle of moment states that total anticlockwise is equal, moments is equal to total clockwise moments. We know that, alright, which is equal to force times distance, As I said to you, because you have two different force, you will get two different force over here, so you can basically write, and they are on the same side, you can write two force times distance equation. So that means that then force times distance plus, remember say a total, plus force times distance is equal to force times distance for that one over there. So force times distance there times seam distance, and then now beam force times seam distance is equal to, so we get moment's principle to be obeyed, is equal to the force times distance over here. Alright, can we get that done? You can rewind, have to erase it for space. Alright, so let's set this up. So I know that my 1 Newton force, my bracket, obviously, my 1 Newton force is a certain distance. Is it 8 meters away from the pivot? No. If you stop at 8 meters, you will never reach the pivot, because that is the pivot there. The total distance of this 1 Newton force away from the pivot is the 8 meter plus the 4 meter, which is also the distance from the center of gravity. Alright, that's why they incorporated it and told you also. So therefore that's 1 Newton times 12 meter. Alright, plus, let's use x to represent the unknown weight, which is the unknown force that we're trying to find. Right, so x times, and the weight that is acting on the center of gravity is 4 meters away from the pivot, times 4 meter. Alright, good. Bracket that, which is equal to, so the total of them over here shall be equal, or must be equal to, and when we check is supposed to equal to, else me answer wrong if it not equal to the 5 Newton times beam distance away from the pivot, which is 6 meters. Okay, can you see that 6 meters right there? 6 meter. Okay, wonderful. Alright, so what the best thing to do when you're in a situation like this, as I have said, right, is to work out the side where your unknown is not on. Therefore let's work out that side first. 5 6's we know say that are 30, right, and that's 30 Newton meter, as a 5 Newton did it. So alright, so 30 Newton meter is equal to 1 times 12, how much? 12 Newton meter, plus bracket again x plus 4 meter, coming out done with it yet. I am not finished with it as yet. Okay, now can I just go ahead and add this to this over here? No, I cannot. Can't do that, because the 4 is adding to the x. You understand where I come from? And because the 4 and the x is not the same kind of unit, can't just do it. So what do? You ask yourself the question, what is the 12 Newton doing to the x plus 4 meter? Obviously it is being added to it. Therefore, to get rid of the 12, then I must subtract it from this side. So 12 subtracted from 12 Newton meter. Cancel him over there. So 12 and 12 are 0. No? So if I do that on the same side, I have to come and take him back from 30. So 12 Newton meter from 30 Newton meter is equal to 18 Newton meter. 18 Newton meter. Okay? Good. I'm not done yet. You understand where I come from? Now I can say 18 Newton meter, take out the bracket there, so equal to x plus 4 meter. X plus 4 meters. Okay? So what do? You ask yourself a question again. What is the 4 doing the x? Because your objective is to make x the subject of the formula. So you have to get rid of the 12, right? Don't touch it yet. Don't go there and add it to the 4. Never do that. You look at what is farthest away, or not dealing directly with the x, and you deal with it first. Like you deal, him a first priority, I'm first to deal with the x. Him a second priority. So you deal with second priority first, and then left first priority for last. Okay? So therefore now you say to yourself, this x is being added to the 4. Therefore 4 has to go to make x subject of the formula. So I eradicate, so I subtract 4 from 4 meter from this side. Cancel it, and I come over here and I do it again from 4 meter. So 18 minus 4 is equal to 12. And now the meter cancels the meter, right? And that leaves me with, oh my apologies, it was x times 4. X times 4 from right there, right? So I do not divide it. After I take out the bracket, I will have x times 4. I do not subtract it rather. So x times 4 will be equal to 18 Newton meter. Therefore, that's meter. So ask yourself, what is the x? What is the 4 doing to the x? It is multiplying. Therefore, I'll have to divide it by 4 to get rid of it. By 4 meter. That cancels that. 18 into 4 goes 4.5 times 4.5. So 4.5 Newton. 4.5 Newton, okay, would be the answer. And then now you say to yourself, that is my weight. So the weight of my rod is equal to 4.5 Newton. Do you understand where I'm coming from? Alright, so say for instance, so the question they done, as me give you, it done, right? 4.5 Newton. But suppose the question had also said they want the mass of the rod. What would you do? Suppose if they never ask weight and they ask the mass, right? Would you get all start crying, start fuss, how you going to do the question? No. You should have known, say you're supposed to can move from weight to mass. You should have known, say a moment's question. Always I go deal with film thing them in a force, which is the weight. And therefore, you know, say you can use moments for you can use moments to get weight. Then you can move from weight to mass. It is that easy. And you'll use back your triangle. Say they ask for mass. Find mass. Alright? Find mass. Let's find the mass of the rod. We know the weight, let's find the mass. We know, say, weight is equal to mass, right? Multiplied by gravity, which is 10 Newton per kilogram. This should be in kilogram. Okay? So, we know the word triangle. We know, therefore, that if we have the weight, up here so, then we find the mass. All I have to do when we cover mass. That tells me that I must, obviously, you know, so this. We know that I shall have to divide my weight by my 10 Newton per kilogram, which is my gravity. You always know that gravity is 10 Newton per kilogram. Therefore, I take my 4.5 Newton and I divide him by 10 Newton per kilogram, which is gravity. This cancels this and leaves me with kilogram. So therefore 4.5 into 10 gives me 0.45 kilogram, which is the mass of rod. Understand, guys? So very easy, very straightforward. It just takes you some small working and some practice. Change up the value them man and work out the value. You understand where I come from? And practice, it makes perfect. Strengthen you in a maths too. Alright, so let us look at this question. Right, and in this question we are seeing that it is very different from all of the other questions that we have observed. We have never seen in any question where there is an upward force. We have always been seeing forces in a downward direction and the thing, right? Pivot down, right? So we have never seen any with an upward force. And we are not seeing directly, straight off the bat, you're looking at it, you're not seeing the pivot also. You're not actually seeing how you could easily do it, right? So I want to tell you though, it's a very easy question and it's the same principle of movements that you're going to follow. So it says a tension wire is used to support a beam that is hinged to a wall. Determine the tension in the wire. In the diagram, it gives you everything that you would need to calculate the missing force that is in F. Alright? Now, a tension wire is a support wire. It is used to support or anchor objects, especially that need to be suspended in the air. Okay? So, the tension wire will be bolted into the ceiling and it bolted into the object as well, and it is suspended from the ceiling. The thing though is attached to a wall, right? It's also hinged to a wall, and when you hear the word hinge, it should pop in your mind that, hey, wait, that right there is my pivot. That's my turning point. Okay, so there's a pivot right there. It is the hinge. Okay, right here a force is acting that is 300 Newton. Right, a 300 Newton force, like a piece of board or a piece of water bucket is placed there, right? 300 Newton weight, and that has a distance of 0.2 meters, all right, away from the pivot. Now the 150 Newton, you could imagine that something else is put on it, like a box of apples, as also is 150 newtons, and that is 0.5 meters away from the hinge. So we know that 300 newtons weight on the slab is 0.2 meters away. We know that the 150 Newton weight is 0.5 meters away. And we know that our missing force here, that is going to be the tension force in the way. And I would like to remind you that when we were doing forces, I wrote on the board that tension is a type of force. Not true. And it is a pulling force, a force that pulls. Remember that. So tension is a force. So what is the tension in the wire? Right? So this is the wire right here, and there is a tension force in it. Right? And it aids to support this thing from not collapsing and going in that direction. Alright? So that's what it's there for. We know that the force here, though we don't know it, it is a distance of 3 meters away from the pivot. There's the arrow, 3 meters away from the pivot. Now, how do we do this question? Where is my anticlockwise movement, you might ask? Where is my clockwise movement? Since, as I had said, that you're going to be using clockwise movements is equal, anticlockwise movements rather is going to be equal to clockwise movements, right? Looking at the thing, the forces that go in a downward direction are going to be your anti-clockwise movements. Whenever the force is going the opposite, these forces are going opposite directions to themselves, okay? So though one is going down and one is going up, this is going to be your anti-clockwise movements, and that is going to be your clockwise movements. Always, for me to go up, it's clockwise. For me to go down, it's anti-clockwise. In questions like these, don't get it mixed up with the rest, because I see two of them are good down, right? But this situation is different, as these things are not, these forces are acting against each other. One is going down, one is pulling up, okay? So, and the hinge is actually anchored into something like a wall, okay? You still have a 90-degree activity going on, right? See how your force edge is 90 degree from the pivot, right? 90 degree, and see here again, still 90 degree from the pivot. So the distances are measured from the pivot also, and the forces are actually acting perpendicular to the pivot. So you know that force, that the moments principle is going to be established. And the thing is also in equilibrium. When you see it in equilibrium, it is actually balanced. Therefore, you know you can go ahead and use the moment calculation principle. Alright, so let's do that. Let's calculate this thing. Alright, so let's see. We said that this is going to be your clockwise movements, and these are going to be, since as they're going in the same downward direction, they're going to be our anti-clockwise movements, right? And they are measured from the pivot to be 0.2 meter for the 300 Newton and 0.5 meter for the 150 Newton. Alright, so we say good. We can also say that we can add these two forces. We can add these two. The moments that is found for this one and the moments that is found for this one can be added. You can't add the forces, you can only add the moments when you calculate them. So therefore, if we have two different forces here with two different distances, we can calculate two moments. So our total anti-clockwise moments will be, okay, we can write out force times distance equal force times distance times force times this plus force times distance is equal to force times distance that we will find over here also for our clockwise moments, right? So let's do that now. Now the 300 Newton has a distance of 0.2 meter. So 300 Newton times 0.2, right, close bracket, plus 150 Newton times 0.5 meter, right, times 0.5 meter. Let me put in my units. Is equal to, right, another force times distance, which is our clockwise movement, which is that upward one right here, x force, x newtons, because we don't know the force, that's what we're going to find, but we know the distance is 3 meter times 3 meter, right? Therefore, so let's work out this part. So as I said, that was 300. So 300 times 0.2, what is that value? Alright, so 300 times 0.2, that is going to be 60 Newton right there, right? And 150 times 0.5, you know that half of 150 is 75 newtons, right, is equal to x times, and this is plus together, right, x times 3 meter. Now 60 plus 70 is equal to 135 Newton meter, right? So 135 Newton meter is equal to x times 3. Let me erase this, get more space. You can rewind if you want, right? So bringing all of that up here now, right? So 135, just erase everything. So 135 Newton meter is equal to x times 3, x Newton times 3, right? And we do not know the force, so we call it x, but we know the distance of it, alright, and we know that it is our clockwise moment. Therefore, 3 is multiplying the x. Therefore, to get rid of the 3, we have to divide by 3 to cancel it, right? Good. And basically, and this was 3 meter, and we do the same thing over here. So meter, cancel meter, 3 into 135, therefore x is equal to 3 into 1 35 is going to be 45 newtons. Okay, therefore the force here is 45 newtons. So that is how you do questions like that. If you ever see an arrow going up, don't pay no attention to, let me sketch a little one. You see questions like these, when you have a pivot, right, you have one arrow go up, one arrow go down, one arrow go down, right? Don't get tricked, trust me, don't get tricked. Two of them are going to be your anti-clockwise movements this time, alright? And that one is going to be your clockwise movement because they are going in different direction. Okay, so remember that when you're looking at your questions and work it just like how I have worked it. Alright, be blessed.